Drive oder wenn mir eine Aufgabe im Planner zugewiesen wird. Irgend sowas kann dann automatisch einen Flow starten. Dann gibt es hier die sofortigen Flows, die werden manuell ausgelöst, indem ich einfach darauf klicke, am PC oder am Handy, und noch geplante Flows, das heißt einfach nach Datum. Wenn ein bestimmtes Datum eintrifft, dann wird eben dieser Flow automatisch ausgelöst. Beginnen wir mal mit den automatisierten, die durch ein Ereignis getriggert werden. Und da möchte ich mal hier als Beispiel Microsoft Forms benutzen. Das heißt, wir haben auf unserer Webseite eine Formsumfrage für Interessenten, die da ein Angebot anfordern können und eben eine kleine Bestandsaufnahme machen und sagen, ich habe folgendes, bitte stell mir dazu ein Angebot. Das heißt, ich nenne es auch mal hier Angebot erstellen. Ich möchte nämlich immer dann, wenn ein Kunde das Formular ausfüllt, dass mir automatisch im Planner eine Aufgabe angelegt wird, dass ich dann eben die Aufgabe habe, dem Kunde das Angebot zu erstellen. Also, was ist mein Trigger, der meinen Workflow startet? Immer dann, wenn ein Kunde unsere Bestandsaufnahme ausfüllt, dann möchte ich, dass ich eine Aufgabe entsprechend im Planner bekomme. Erstellen. So, also wenn eine neue Antwort da ist in Forms, dann muss ich erstmal sagen, in welchem Formular. Das heißt, ich gehe hier mal rein, dann werden mir meine Formulare hier entsprechend angezeigt. Ich sage, das ist dieses Formular Angebot. Also wenn da eine neue Antwort eintrifft, dann soll mir im Planner eine Aufgabe angelegt werden. Da schauen wir mal, ob wir das finden hier. Planner. So, ich gebe es mal ein hier. Planner. Jawohl, das geht. Und hier unten wird mir sogar schon das angezeigt. Aufgabe erstellen. So, jetzt muss ich die Details hier natürlich noch entsprechend auswählen. Also in welcher Gruppe. Mir geht es hier um einen Plan in Gruppe Büro Kaizen. In welchem Plan? Geht es um den Vertriebsplaner hier. Dann kann ich den Titel hier entsprechend auswählen. Das sage ich einfach mal Angebot erstellen. Und das ist aus der Umfrage. Und hier kann ich noch so diese Antwort-ID nehmen. Also welche Antwort ist es? Wenn man mehrere Antworten hat, hat jede eine ID. So, dass ich weiß, um welche neue Antwort geht es. Das passt. Und ich muss natürlich noch sagen, jetzt um welchen Benutzer geht es hier. Also soll immer eine Aufgabe für mich erstellen. Wunderbar. Ich speichere das Ganze mal. Und so einfach geht's. Jetzt, sobald ein Kunde bei uns auf der Webseite auf den Link klickt und unser Formular für Neukunden ausfüllt, bekomme ich automatisch im Planner eine Aufgabe erstellt, dass ich dem Kunde entsprechend zu seinen Angaben ein Angebot erstellen soll. Ich könnte auch noch weitere Dinge jetzt hinzufügen, weitere Schritte und sagen, schick mir dazu noch eine neue E-Mail, wo ich noch informiert war oder irgendwas anderes. Also man könnte da auch jetzt hier entsprechend mehrere Schritte noch in diesem Workflow definieren. Als nächstes möchte ich mal einen sofortigen Flow, den man manuell auslösen kann, anlegen. Wir klicken mal hier drauf. Also, da kann man zum Beispiel jetzt Kollegen oder Dienstleister über ein Ereignis informieren, als ein Beispiel, indem man das manuell auslöst. So, Druckerprobleme zum Beispiel erstellen. Löse einen Flow manuell aus, neuer Schritt. Ich möchte jemanden per E-Mail informieren, neue E-Mail senden und sage hier einfach mal zum Beispiel, Druckerei hat eine Störung, bitte beheben. Und als Tipp, laden Sie sich mal die App von Power Automate auf Ihr Smartphone runter und wenn Sie solche Dinge machen, manuelle Flows über eine Schaltfläche, dann können Sie die mit einem Klick in der App einfach auslösen. Richtig gut. Und dann können Sie Dienstleister, Kollegen informieren über Ereignisse, die öfters mal auftreten. Zum Beispiel Drucker 3 funktioniert nicht. Mit einem Klick auf dem Smartphone bekommt die Technikabteilung den Hinweis, bitte schaut mal nach dem Drucker 3. Als letztes möchte ich noch einen geplanten Flow einrichten. Ich klicke mal auf geplant. Und was will ich hier machen? Natürlich kann ich mich jetzt erinnern lassen an Dinge wie einen Hochzeitstag und so weiter. Das geht aber auch über den Outlook-Kalender, dafür muss ich keinen Flow einrichten. Ich möchte hier mal meine Kollegen an etwas erinnern, und zwar, dass sie jeden Freitag ihren Wochenbericht abgeben. Also ich nenne den Flow-Name mal Wochenbericht. Und wann soll der gestartet werden? Der soll jetzt diesen Freitag gestartet werden. Morgens um 10 Uhr ist okay. Ich möchte ihn wiederholen, einmal pro Woche. Und zwar immer am Freitag. Das heißt, ich mache die anderen Tage mal raus. Dann werde ich jede Woche am Freitag erinnert. Oder nicht ich, sondern die Kollegen in dem Fall. Gut, wir haben die Erinnerung angelegt und sagen jetzt als nächsten Schritt, wir wollen auch hier eine E-Mail verschicken, könnten auch eine Teams-Nachricht verschicken, eine E-Mail verschicken hier an die Kollegen, geben die Kollegen ein und sagen, bitte Wochenbericht bis 16 Uhr abgeben. Danke. Unter dem Menüpunkt Meine Flows bekomme ich auch jederzeit noch eine Übersicht über alle meine Flows, die ich bereits angelegt habe. Man sieht hier jetzt meine 4 Flows, die wir angelegt haben. Ich werde informiert bei bestimmten Tweets in Twitter. Ich bekomme eine Planneraufgabe, wenn eine Formsumfrage auf der Webseite bei uns beantwortet wird. Ich habe hier einen Flow angelegt, den ich vom Smartphone aus mit einem Klick in der App starten kann über Druckerprobleme. Und wir haben noch eine Erinnerung angelegt jeden Freitag für die Kollegen zum Thema Wochenbericht. Man sieht, Microsoft Power Automate ist relativ vielfältig, kann da ganz viele schöne Dinge automatisieren und deswegen sollte man immer drüber nachdenken, wenn man Dinge immer wieder auf die gleiche Art tut, kann man das nicht vielleicht mit Power Automate irgendwie automatisieren, um sich diese Arbeit zu sparen. Mich würde auch sehr interessieren, wenn du schon Power Automate nutzt, was hast du für Flows im Alltag, was hast du für dich automatisiert? Würde mich freuen, wenn einige bei den Kommentaren da ihre Erfahrungen reinschreiben und wenn du vielleicht unseren Kanal noch gar nicht kennst und jetzt nur dieses Video gesehen hast, wir veröffentlichen jede Woche ein spannendes Video zu Microsoft 365 Themen. Abonniere gerne unseren Kanal, wenn dich das Thema interessiert. Ich wünsche euch eine gute Woche und bis zum nächsten Video. Ciao!
also takes a message called MIDI note that is specifically designed for situations like if you're receiving notes from a MIDI keyboard where you get one message when the note starts, and some indeterminate amount of time in the future, the pianist's finger comes off that key and that note is now off. But you didn't know in advance how long that note was going to be. So before I get into the somewhat detailed way that I integrated that with our audiovisual sine wave synthesizer, I'm just going to show a very simple example. So this is a thing called use polytilde with MIDI note, and I made this thing called pretend MIDI synth. So I'm going to open all 3 instances of it, and this is a pretend MIDI synth because it doesn't actually make any sound. It just tells you the key number and the velocity that it is, quote, playing. But it has all the same this poly mechanism so that it knows whether or not it's busy. So these are voices 1, 2, and 3, as you can see, because those numbers came out of the this poly objects, and also again because in the title bar of the window there's a 1, 2, and a 3 here. And you can see that all of these are currently muted and not busy, all 3 of them. So here's a K slider, a sort of fake keyboard, and I'll click near the top of this middle C, and that is a note with key 60 and velocity 110. So now this left pretend MIDI synth, let me just change the size of this a little bit so we can see them all at the same time. So now this imaginary middle C is sustaining, and this voice number 1 is still holding that note, and you can tell because it's still busy and not muted. And then when I release that note, then the list 60 got sent into this particular voice, and it went back to being muted and not busy. So what happens if we hold down multiple notes? So here's a quieter C, velocity 40. Here is a loud E, and because this voice was busy, Poly, when it got another MIDI note message, it picked voice number 2 as the first free voice. So now if I let go of the C, then polytilde remembered that this object, the first voice inside it, was playing key 60. So when it got the 60, it dispatched the 0 to that voice that was sustaining that middle C. So now if I ask for another note, 55, the voice 1 is free and that came out, so now there's 2 notes happening, and then this high B flat, this MIDI 70 is 1 and 1. So now we got a 3 note chord held down, we got all 3 of our voices busy, and if I let go of a voice, the key point is that that same 64, the key number that turned on this note, the same number came again and turned off that note, and now this voice is free again. So that is a sort of MIDI style way of handling polyphony, where you use one message, the note list, to turn on a note, and then a subsequent message with a 0 velocity to turn off the note. Saying all this is making me wonder, if I were to send the list 60, 65, let's say that I turned on, let's turn all these off. So let's turn on note 60 with a low velocity. That's 21. What if I ask for note 60 again with a higher velocity? It went to a separate voice. So now I have sort of 2 copies of the same note sustaining. And how does it know if I send it a 60, it's just gonna have to pick. It can't tell which note is which. If I send it a turn off message, it, I guess, turned off the first one that it found. And if I send another note off, it turns off the second one that it found. So if you send multiple MIDI notes with the same key number, you are getting multiple voices playing that same key. And then you need that same number of note off messages to free them all up. So let's look at how we can apply this MIDI note feature of the poly object to our audiovisual sine wave synthesizer. What MIDI note does is it keeps track of note ons and note offs for you. So remember in the MIDI protocol, one of the things that we saw when we were using my trigger finger device is that even though the device outputs one message when you press the pad, and it waits until you let go of that pad to send the note off message, the way that we had built the synthesizer, where we had to know in advance the duration of the envelope, prevented us from being able to use the note off message. So we were just throwing away the note off message, but not anymore. So here you can see I've got a trigger finger object here, and you can see that there isn't a trigger finger device on the table here. So I'm just going to use it in its virtual mode here, and let me show you the behavior before I show how it achieves that behavior. So I'm holding down that note, and that note lasts for as long as I hold it down. And then when I let go, it lets go. So I'm using send and receive to set the attack time. It's kind of satisfying to have a short attack time so you get a sort of percussive sound and maybe a nice long release time. I'm still holding down the button. The note is still sounding. Max doesn't know how long this note's going to be. No one can predict when I'm going to let go of this mouse with my finger. There, I just did it. And so it's releasing away. And of course, if I only have one mouse, but if I had the actual hardware device, I could hold down multiple pads and we could hear it in polyphony. Maybe I'll do that in a moment. But first, I'm going to show you how this works. So I take in a note and I take the velocity and I convert it into gain on a decibel scale, just like before. But I also need to pass the velocity as an int, because one of the features of this MIDI note message that polytilde can accept is that it looks at the second argument of this list, which is supposed to be MIDI velocity, and it knows that a velocity of 0 means a note off. And so it's going to use that to handle the keeping track of who's busy and who's not. So when I get a message out of trigger figure that says a certain pad was pressed with a certain velocity, I convert the velocity to a gain, I leave the velocity alone, and I convert the pad number to a frequency, so that my note list looks like this. Not MIDI key, that's an error. My note list looks like this. It's the frequency in hertz, the MIDI velocity, which all that really matters is whether it's 0 or non-zero, and the gain in dB, which is what's truly controlling how loud each note is going to be. So what does this look like? Sine blip voice off later. So that means that you turn it on now and you'll send another message in the future to turn it off later. That's how I chose that name. And I'll make it a little bit shorter so we can fit it on the screen here. So what's happening here? This is a very different layout from what we had before. So first of all, there's still a cycle object. Its frequency is still set by the first element of the note list. It's still multiplied by an amplitude envelope that comes from the line tilde object, and that's what goes out to output. That's all the same as before. But now the attack portion and the release portion are being triggered separately. So I'm using, again, send and receive to set the duration of the attack and the release. So these are global to all of the notes, and I made them default to 300 milliseconds in each case. So let's look now carefully at what happens when a note comes in. So we're unpacking this note list. The gain is being used along with the attack time to set the attack portion of the envelope. So if our gain is negative 30 dB in linear amplitude, that's 0.032 something. And so we make the list of that linear gain 0.032 something over 50 milliseconds. And we save it in this message box, but we don't necessarily bang it. We put this value in here, and it's waiting to possibly be banged. So now we look at the MIDI velocity, this integer that's the second element of the note list, and that's either an on or an off. So meaning it's either non-zero or 0. And here's a selector that is looking for 0. So if it's 0, then we do some stuff that I'll explain in a minute to turn the note off. If it's non-zero, we do some stuff to turn the note on. Namely, first of all, we keep track of the fact that we just became busy. So this is the I'm busy and I'm unmuted message that we saw before. So as always, before you start playing a note, the first thing you do is you close the office door and say, don't bother me, I'm busy. And then since it's a note on, we're going to actually send a bang into this message box that we just created. And that is going to go into the line tilde, and it's going to make the attack of the note start. So the amplitude is going to start climbing up. And when it reaches its maximum, a bang comes out of the line, but that's going into a one bang object that we haven't put anything in the right inlet yet. So notice, even though we just hypothetically got to we completed the attack portion of the envelope, nothing's coming out of this one bang. This is selecting just the end of the release segment. So how does that work? If it's a note off, then we open up this one bang. We say, okay, the next time line outputs a bang, I want it to come through you. And then we send a message over here to this pack that says go to 0 amplitude, go back to silence over the amount of time that's the release time. And that goes into the line tilde object. And then it's decaying, it's going to nothing. And then finally it gets to 0, possibly over a very large amount of time if your release time is long. But once you get there, line outputs a bang. And there had been, let's see, if this were an off, then well, there it just happened. So line output a bang, and it got through the one bang because we turned it on when we
Sadly, it's not possible to play at 4 times the speed. This one only allows 2.5 times the speed. YouTube only allows 2 times the speed, so maybe this is what's throwing you off, the 0.5 times more speed than usual. But it's quite normal speed, I'd say.
Determine this was a node off. And then what happens, so this means that the node is over, and so of course that means we go back to not being busy and to being muted. So that's how it works. So now, we don't need to know in advance how long the node is going to be. We turn on the node, it fades in, and it just holds there for however long we want until we send another message to turn it back off. So I just showed you how to synthesize a note whose duration you don't know in advance. One thing that I haven't done is draw a squiggle whose length we don't know in advance. So you can see here I just disconnected the graphics. So this note list that used to be going into the graphics object, I just disconnected it. You could use techniques like this to sort of start drawing the thing and just kind of keep adding more and more points to it for as long as the note is sounding and then stop when it's done. Or maybe you could keep track of how long the note turned out to be, and then after the end of the note you could draw the squiggle that has that duration. There's all kinds of techniques for dealing with that, but I'm not going to bother.
Oh yeah, good point, yeah. Just, wait a minute, can I download it? Yeah, I can download it. I'd say, oh, I can download it even officially, and I just didn't realize that. I thought I'd need the special player thing. No, I'd say 2.5 is enough, is sufficient, I'd say. You know, we don't need, let's keep it simple, let's keep it basic and relaxed, you know?
Doing these things, I just took the easy way out and just disconnected the graphics. Next paradigm I want to discuss is related to what's known as constraint programming. So strict constraint type programming, like what this Wikipedia article is talking about, is a way of programming where instead of saying do this, then do this, you say these two pieces of data have the following relationship. And then the programming environment sort of figures out for itself, based on what's been specified, how to determine the values of everything else in a way that satisfies the constraints. So I'm not aware of a way to do that in that way in Max, but what you can do in Max is much simpler, and in some ways it has somewhat similar effect, which is that you can have, so this is sort of the way that it should work. So this is a Celsius to Fahrenheit converter. So I can put in any temperature here in Celsius, and it goes to Fahrenheit, and it also works in the other direction. So it can also be a Fahrenheit to Celsius converter. And but instead of just saying this is a relationship between Celsius and Fahrenheit, I just said very much explicitly, if you have a number that's a temperature in Celsius, then do this arithmetic to make a number that's in Fahrenheit, and then I manually sort of did the inverse function here to convert back in the other direction. And you saw this before, you have to break the hot inlet triggering computation. If you just have a loop like this, then you're going to get a stack overflow. So that's why when we saw a similar thing before, you have to somehow break this loop. So that's what this set does. So when I change the temperature in Celsius, this message box outputs goes into this expr to its hot inlet, and so expr outputs a new value, which is the value in Fahrenheit. And when that number changes, it goes into this expr. But the output of this expr is going through this message box that's adding the word set in front of it, so that if I put a value into this set, it changes the value that's displayed in this number box, but nothing comes out of it. So it's only when I move this number box that it outputs. If I move this number box, it changes what's displayed, but doesn't make it output. So this set sort of breaks the infinite loop that was causing a stack overflow. We saw a somewhat more sophisticated version of this back when we were talking about scales and tuning, where I made this thing a ratio to sense converter. And I explained this technique there. I'm just going to review it here because it's topical. So the number of octaves of an interval, if we set it to 1 octave, then 12 times that is the number of half steps, and we've got a set. So any of these things, if I change them, whether it's a frequency ratio or the number of cents or a frequency ratio divided by 2 or any of these things, anything that I change is going to trigger some calculation that is going to set the number of octaves. And when I say set, I shouldn't say set. It's going to send a message that is going to actively put a new number into this number box. And then this number box will output this 2.14243 octaves into all of these different places that are converting this musical interval into all these other ways of describing the same interval. And in every case, I've got this set that is preventing an infinite loop from happening by making it so that these number boxes display the current value, but they don't then output. So it's not constraint type programming at all in the sense of you just specifying the constraints and the programming language magically satisfies them, but it's in the style of constraint programming in the sense that you can sort of change any of these values and all the rest of them will update automatically. I mentioned several times that Max excels at interactive real-time processing, but I'm also going to show you a style of programming in Max that is non-real-time. So what do I mean by this? So in real-time processing, time is advancing, and every time something happens, Max tries to respond to that as quickly as possible and make the output happen in time in relation to when things happen in the input. Non-real-time processing is the way most software works, where you run the program and it just cranks through the data as fast as it can until it can come up with the final answer. So for example, if you're rendering a movie in some kind of program like that, it takes a certain amount of time, and if it's able to go faster than the speed at which you watch the movie, that's great. It only took 1 minute to render your hour-long movie. You don't want it to necessarily take a full hour to do the job if it doesn't have to. And likewise, if you're doing something incredibly complicated, like maybe you're Pixar and you're rendering a movie, and there's absolutely no way that you could do all that processing in real time. They have huge server farms that are, each computer takes hours and hours and hours perhaps to render one single frame of the movie. But of course, they don't want to make their movies look like video games and compromise the quality of the graphics to get it down to something that they can compute in real time. They compute it in non-real time. So they take as long as it takes to get the right answer, in this case, a good-looking frame of a movie, and it takes as long as it takes, and when it's done, and you've got the data. So I'm going to show you how to program in Max with that kind of style. So my first example is extremely simple, almost comically trivial. It's called times table.maxpat. So if you're like me, when you were a kid, you had to learn all the products of all of the integers from 1 to 12. So this object prints in the Max window the whole times table from 1 up to 12. So we learn from this the fascinating information that 1 times 1 is 1, 2 times 1 is 2, et cetera, et cetera, et cetera, et cetera. So it's telling me all the pairs of integers from 1 to 12 and from 1 to 12 and what's the product of those two numbers. So how does it work? I have two Uzis that are talking to each other. So when I hit this bang, this Uzi, first it outputs a number, starts at 1, and I put that into the cold right inlet of this times object, and then I also put it into the cold second inlet of this sprintf object, because it's going to say something times 1 is something. And then after I put that 1 into here and here, the bang comes out, bang number 1 from the Uzi, and that bang causes this Uzi to output its 12 numbers from 1 to 12, and for each one I put it into the hot left inlet of times, and so we multiply, in this case 1 times 1 is the first one that happens, and that goes here into the cold right inlet of sprintf, and then I take this number 1 that is the left argument to times, and I put it into the hot left inlet of sprintf, and so it says 1 times 1 is 1. Then this Uzi goes to 2, and it says 2 times 1 is 2, et cetera, et cetera, et cetera. You know how the story ends. So the idea here is that Uzi goes as fast as it can. So when this Uzi outputs a number, number. However much processing happens as a result of outputting that number happens. The whole story about stack frames and all that, and there could be a long series of complicated computation that may take your computer an hour to deal with this one that comes out. But no problem, it takes an hour, and then after that hour is up, then Uzi gets a chance to do its job, it outputs this next number, and so on. So this is going as fast as possible. That's why it's called Uzi, because it bangs quickly. So let me show you a more musical example. Same exact technique using Uzi. But now I am computing the pitches of the notes of a scale. So I am making a pentatonic scale. So I have this collection that is giving me the 5 frequency ratios of the 5 notes of a just in tone pentatonic scale. So we've got the tonic, which is 1, which is the base note that we're using, and then we go up to 1.125 times that frequency. That is 3 halves times 3 halves divided by 2, 9/8, a Pythagorean major second, and then this is a 5/4 just major third. This is a 3/2 perfect fifth, and then this is a 5/3. Am I right? Yeah, 5/3 major sixth. So these are the ratios within 1 octave, and I made this Uzi count up to 46 so that it would have a large number of octaves, I guess 9 octaves, and starting at the tonic, which in this case is C1, but I could change it to some other thing, how about F sharp, why not? And we'll hit it again. And so what's it doing? Every time Uzi counts up, it outputs the number. I'm converting to 0 origin. For whatever reason, I'm printing out all these numbers, so we can see in the max window just all the numbers from 1 to 45. That's not too exciting. Not sure why that's there. So what do I do with each of these numbers? I bang the base frequency, and I use that as something that's going to be multiplied. I take that number modulo 5, and that tells me which scale degree it is, 0, 1, 2, 3, or 4, which is conveniently the index that is looking up that number in the scale. And then I multiply those together, and then that's stored in here. And then I take that same number, and I divide it by 5, and that's telling me which octave I'm in. So these 5s here are, because of the fact that these are pentatonic scales that have 5 notes per octave, you have to change that. There are different number of notes per octave. And then I take, depending on what number this is, let's say the number is 20. Well, 20 divided by 5 is 4, so that tells me we're in the 4th octave. So 2 to the 4th power is 16, so that's another thing that I multiply that by. So at the end of the day, the result of this is the frequency in hertz of this note of the scale, given that we started here and that it repeats at the octave, and that within each octave it uses these intervals. And I'm writing them using a peak tilde object into a buffer that I've got named pentatonic. So that's right here. And I made this as a very short sound buffer. It's only 46 samples long, but I'm actually not using it for sound. I'm just using it as a lookup table, so that later on I can just put a number into peak, and I can say what's the 10th frequency in this table, what's the 11th frequency. So these aren't meant to be interpreted as audio samples, they're meant to be interpreted as frequencies, which is why I'm putting them into the saw object. And so having done that, I can now move my way up and down the scale. So it's a very, very low pitch, 46 hertz. I'll use some reverb, and I got some instant new age music here. Pentatonic scales are very, very pretty. Let's turn our attention to a more difficult, or at least more computationally intensive problem, which is processing video and outputting a movie. So there happens to be a tutorial, number 19 of the Jitter tutorials, called Recording QuickTime Movies, that has a nice explanation of this. I'll take it in order, but the part that relates to non-real-time processing is this number 3, offline recording. So let's go through the sequence of the 3 points of this tutorial one by one, and we'll get to this last one, offline recording, and you'll see what I mean. So basic recording uses an object called jit.record, which when it's not recording, it outputs the same matrix that it receives. So here we've got a jit.movie that's playing countdown15.move. And we're passing it through this jit.robcross object, which is doing edge detection using a technique discovered by a researcher named Rob Cross. That's where the name of this object comes from. And if we want to save, let's stop this. And we'll stop it right after it gets to 1, so we start moving at the right place. A little bit more, stop. Okay, so here's on 10. So now if I say write, and I give it some arguments, which aren't that important, then it asks me where I want to write this to. So I'll put it on the desktop, I'll call it edge detected.movie. And if this goes, start, then you see that nothing's coming out of the jit.record object. I meant to connect this actually to the output here, so we can see that this object is still doing its job, and the jit movie is still doing its job. 5, 4, 3, 2, 1, stop. Okay, and as soon as I stop it, the jit record is again outputting what it receives on its input. I can turn this off, and now if we look over on my desktop, there it is, edge detected.movie, and it starts at 10, and it goes down, blah, 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 and you'll see that it ends right at that moment that it just received 10 when I clicked off. So this is what you call real-time recording. So everything's happening in real time. The movie's playing, we see it counting down at 1 second per second. We could interact with it, we could change the parameters. As the movie's recording, we can do anything we want, and luckily all this processing, it takes up a small fraction of the capability of this computer, so each frame is able to be computed in a timely fashion, and no problem, everything happens in real time. So if you can do things in real time, that's great. Let's look at the next example. Advanced recording, very similar idea, except this time we're going to do more processing. So we're going to use jit.hatch, and we can set the grid size. So here's our same movie, we're playing the movie, and we see the output of this jit.hatch is this kind of cool crosshatch effect, and we can set the number of pixels of spacing of the grid that we want to use. So there are 3, there are 11, etc. And we can ask the movie what its frame rate is right here, by saying get FPS, and it'll tell us that this input movie has 15 frames per second. So we can tell the right message that it should record a movie that's 15 frames per second. And we can also take this frames per second and divide 1,000 by that to find the number of milliseconds between each frame, and we can have this metro bang this jit matrix through 0. So what's happening here, this is a matrix that's holding the most recently computed video frame. So this movie might be going faster or slower. This jit.hatch might be so expensive that it's running at a lower frame rate than the 15 frames per second that we are trying to get. But it doesn't matter, because 15 times a second every 66.2 milliseconds, we're going to send a bang to this jit matrix. And whether it's a new matrix that we haven't seen before, whether it's still holding the same matrix from when we previously banged it, no problem. It's going to output whatever it's holding right now into jit.record, and that'll be what goes into our movie. So this is a sort of, it's still a real-time style of recording, but it is allowing for the idea that the processing might be happening faster or slower than the output frame rate, and it sort of decouples the output frame rate from both the input frame rate, the original frame rate of the movie, and also the processing frame rate, how fast all of this can happen. Now, jit.hatch is still pretty cheap thing to do, doesn't cost a lot of computer time, so this still all works in real time. Now, what if we want to do some crazy, extremely expensive video processing that we can't do in real time? That maybe if we were trying to do in real time, we would get 2 or 3 frames per second, and it'd be a horrible looking movie, and we wouldn't be happy with it. So that is what this last thing is going to show, and this is bringing us back to the topic of this lesson, which is non-real-time processing. So here's the offline recording, the third of these patches. And it's somewhat similar, but also extremely different. So first of all, inside here is a thing called heavy processing that once upon a time when this tutorial was written was a lot more than Max could do in real time, in a timely fashion. Computers have gotten faster, so maybe we should just make this even worse. Let's add a whole bunch of more blurs. Just I don't know what any of this stuff even does, but I'm going to do it twice as much, just so it'll be more expensive. That's the point of this, it's expensive. Who cares what? Let's see if we can see what happens. So here's our same movie, and if we run the movie at, processing is off. So this movie is running at about 47 frames per second. This metro is trying to go every 2 milliseconds, which would be 500 frames per second, but I think the jit.movie isn't outputting that often. So if we lock the patch and we turn processing on, if we lock the patch and turn processing on. Now you see it's blurry, and we're down to 18, 17 frames per second because of this blur effect. But let's imagine that this were like 1 frame per second and that we were not satisfied doing this in real time, but we wanted to process every single frame of the input movie through this set of heavy processing and make sure that our output had 1 frame per input frame, and that every frame was precisely the right function of the input frame. So you do it with a message called frame dump. So that's it right here, frame dump. So what we're going to do, if we send the frame dump message to jit.movie, I'm going to turn this off because it's distracting. If you send the message frame dump to jit.movie, it's kind of like Uzi. It means output everything as fast as possible, but where as fast as possible also means as slow as necessary. So when you send frame dump to jit.movie, it tells you that it's doing a frame dump, and it'll tell you when it's done, which is what's happening over here, and it will output the first frame, and that will take as long as it takes to process. And in this case, that frame is going through all of this heavy processing, the hatch, the wake, blah, 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 and at the end of the day, it gets put into this JIT record object, and JIT record says, okay, great, I got my next frame of video. And then, maybe it was 1 millisecond later, maybe it was a million milliseconds later, doesn't matter. 1 frame came out of JIT-movie, a lot happened, the result went into JIT.record, great, that was the end of that chain of processing, and then JIT-movie says, okay, here's the next frame, and the next, and the next, and the next. So JIT-movie keeps outputting the frames one by one, and every one of those frames goes through all this processing, and then at the end of the day, the frame dump, the right output of JIT-movie outputs the message frame dump done, and then when frame dump is done, we stop recording, and like that. So that's how you do it. Now, one thing you have to be careful with, suppose you want the parameters to change frame by frame. So that's what's happening here. When I record, I am resetting the counter to 3, and let me just show you that this counter is going back and forth between 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14, 15. So it's climbing up and down between 3 and 15, and it's changing the parameters of this JIT.hatch. It's setting the grid size to one of these numbers between 3 and 15. And it's doing that frame by frame. So I'm not manually changing this number. This number is happening every time JIT record gets a new frame, or every time JIT record outputs a frame. We're converting it from a matrix to a bang using TB. And so this counter is basically keeping track of which frame of the movie we're on. And so each frame is processed using a different value of this grid parameter. So that's how you have to time things. So unlike in real-time processing where you can use all of Max's mechanisms for timing, the metro object, the line object, all these ways that you've seen for making things change in a meaningful way over time, or even real-time input. Maybe you're moving a fader up and down on your MIDI fader box, or however you want to do it. It's very easy in Max to get something to happen in real time. This is the way that you do it in non-real time. So this technique here will guarantee that each frame of the output movie is processed according to whatever time you want. So here, the grid amount is going up and down, up and down, up and down. But you could put anything in here. You could have a counter that didn't have a maximum, that was just telling you which absolute number frame of the movie you were on. And you could have a dictionary or collection that says, on frame 1 of the movie, use these effects. On frame 2 of the movie, use these effects. You could specify exactly what you want to have happen frame by frame, any way you want, using this kind of technique where you're counting the number of frames that have been recorded so far so that you know which frame you're on. And so whether you're going faster than real time or slower than real time, you're not waiting for anything. You're just cranking through all those frames as quickly as possible. So there's some examples of how to do non-real time processing in Max. This next paradigm is quite fun to think about. It's a very meta thing. It is using Max to write Max patches. So Max has an ability that's called scripting that you can access through an object called thispatcher. So let me show you how that works. I made this really awesome example here called scripting with thispatcher that consists of a single thispatcher object. It says open the help patch. So I'm going to do that. It's good advice. So there's all kinds of stuff that thispatcher can do. Like for example, if you have moved something in a patch, you made an edit, then what's called the dirty bit gets set. So this red circle got a little darker red thing on the inside. That means that if you're going to close it, it's going to ask you, do you want to save? Because you made a change to it. Well, you can reset that by sending a message clean to thispatcher, or you can send a message dirty. You can also send the right message to thispatcher. So that's how you can get Max to programmatically cause the thing to be saved. You can change the title of the window. So now this window's title is new name. You can send the message load bang to thispatcher, and all the load bang and load mess objects in your patch will do the thing that they would have done when the patch started. This is the thing that happens all the time. You can ask for a patcher to be sent to the front. Oh, here's a new one called new name. Not sure how that happened. So this is something that I do quite often. So like if you've got a little control panel that shows you some particular information that you need to see only at certain times, and your program knows when those times are, like you're going to the 3rd section of your musical composition, and so you hit like a special key on your MIDI device, and it brings you to the 3rd section. You can from Max, you can bring up the the window that shows you what you need to see for the 3rd section of your piece. So there's a bunch of fun stuff you can do with thispatcher. On this side, you can send it a path message, and it can tell you where exactly on your computer this particular patch is stored. There's a whole bunch of stuff here, but let's talk about scripting. So there is this help patch has been around for longer than Max has had tabs in help patches. So these, if this object were written today, or if this help patch were written today, these would all be just separate tabs up here, like you've seen in a lot of other objects, like receive only has one. Print only has one. Now I'm trying to show you one. Message box. Yeah, message box has multiple tabs here. Tab. But print instead, thispatcher instead of having a bunch of tabs, just has a bunch of patches inside it. So I'm gonna look at this one called making new objects. So you can send the message script to thispatcher, and if the word after script is new object, then it creates a new object. So if you say new object call, then it just put a call object in the default position and at the default size. I can delete that. I can say make an object whose text is call and whose font is 24. So you do that with attributes. You can make an object whose text is trigger BBB, and it can resize, just like if your object is the wrong size and you say command J. What does command J stand for? Fixed width. Right, so you can use this fixed width attribute to make the width be automatically the right length, etc. You can put them in a certain position on the screen. So you can say what the patching position is, and so on. So this is all fully documented in the reference information. So if I go to thispatcher full reference, there is attributes and messages and patcher messages and scripting messages. So all the things that you can put after the word script are all in here, and it can tell you in great detail what happens. But you can use new object to add objects to your patch, and then you can connect them to each other. So that you can do here. So here's some items on which to operate. So one thing you have to do, if you're making objects that you want to be able to connect to each other, then you have to give them a name. So these two number boxes already have names. Right here, they're the scripting name. So this one's called var1, and this one is called var2. So when you can either set that manually in the inspector, or when you create it, you can set its scripting name programmatically. The whole point of all this is that you can do all these things programmatically. The whole idea is that you're not patching manually, you're writing a Max program that can patch stuff together. So you can, for example, make a connection from the 0th outlet of var1 to the 0th inlet of var2, and you see that patch this patch cord just appeared, and we can disconnect that, and the patch cord goes away. So connect, disconnect, connect, disconnect. That's pretty fun. I guess you could animate a movie just by sequencing the scripting of the thing. You can set the color of the connection, etc. There's all these things you can do. So I'm not going to take you in detail through all this. I'm going to show you one example that is the biggest project that I was ever involved with that uses scripting. which is an object that we developed at CENMAT in the early 2000s called multibuff. So we were in a situation where we wanted to be able to deal with large numbers of sound files and load each one into its own buffer tilde object. And we didn't, say you have a folder with 1,000 sound files in it. What you do not want to do is type in by hand buffer tilde sound one, my first sound file.iff, and then you don't want to do that 1,000 times. So the idea was you could put all the names of all, well, I'll show you how it works here, because there's a help patch. I apologize for the low size of the font in here, but for example, well, here's the multibuff object right in the center, and you can see there's a vispatcher object, and you can see there's a collection, and you can maybe guess from the fact that this collection's name starts with a somewhat arbitrary integer that we were using the technique I showed you a little while ago of making the name of the call start with sharp 0, so that each multibuff has its own independent collection in case you want to have multiple multibuffs in your object. But just to sort of go straight to the punchline, let's say that you've got some sound files, like this collection of mat sounds we've been using all along. So if I drag that folder onto here where it says drop folders here, then as if by magic, now inside this multibuff object, there's a buffer named choke.wave that contains that sound and so on. All 10 of these sounds have appeared as buffers, and each of these buffers has as its name the name of the sound file. So if you want to know exactly how it works, and if you're brave, you can open the guts subpatcher, and this is all the scripting stuff. So this is the script connect, this is making the new object, this is sending a message to the buffer so that it loads the sound file, and we're building these messages using sprintf because we want to insert the name of the file. We are deleting the old ones if necessary, etc., etc. This is quite involved. This was actually a group effort, as this help file says here. It's by my friends Ali Momeni and Michael Zavinsky, as well as some contributions from me, and there are several versions of this. You can download this on the CENMAT website. I haven't told you all this. I recommend that you don't use this object because now Max has built in, this is yet another thing that in the old days we had to do for ourselves at CENMAT, and now Cycling 74 provides, which is probably good for everyone. There's an object called polybuffer tilde that you have to give a name to. Mat sounds would be an appropriate name. And you can read a folder, and it makes a bunch of buffers internally. It doesn't use scripting. You can't double click on it and see what's inside, but if you say read folder, you send it the message, read folder. Notice, by the way, that as I start to type into this message box, Max realized that this message was close to this object, and so it guessed that I wanted to type one of the messages that that object can respond to. So if I say read folder and click, and I go to my desktop, and I select mat sounds, and I say open, so now I have 10 buffers named mat sounds 1, mat sounds 2, mat sounds 3, etc. So if I put it on a waveform object, and I send it a message that tells it which buffer to use, if I send it the message set. So if I tell this waveform object that I want it to set to use mat sounds.1, then that's the first buffer that came out of that, and there's a buffer named matsounds.2, and so on. So however many files are in this folder, in this case 10, it made me 10 buffers, and the name of each one is whatever I typed in, dot, number 1, number 2, number 3, etc., etc., etc. So this is the modern way of loading a whole bunch of sound files into buffers all in one, not using scripting. But if you want to see the big scripting project that I personally was involved with, that's why I put this multibuff object in the downloadable resources for this session. You can also load patchers into Max programmatically from Max. There's an object called pcontrol. So I made this kind of a ridiculous patch called plusser that takes an argument and just adds that argument. It's got an inlet and outlet, and it just adds some number to the int that comes in its inlet. And I'm not going to use it, but I'm going to show that there's a lot of things you can send to pcontrol. You can open and close the patcher window. You can enable or disable MIDI within that window. You can open a help patch. That's kind of cool. So like if you make your own help patch and you want to say see also, blah, 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 this other thing, you could make a thing you could click that would open another help patch. But here's the thing that you can really get in trouble with. You can send the message load to pcontrol, and it will load a file. And you can give an argument, and that'll become the argument for it. So I can say load plusser 12, and it just open a new window with a plusser 12, and I can say load plusser 15, and there's that. So here we go. Spin this number box and watch the screen fill with patches. So here's a whole bunch of plussers. Look at the size of that shadow. I don't think I've ever made such a large shadow in OS64. So now if we look at the window, we've got just this ridiculous number of plussers. So you can write a Max patch that loads another Max patch. No guarantees that that's going to happen in a timely fashion. So you might want to be in overdrive mode when you do this, so that other kinds of processing won't slow down. If you're loading a big patch, it takes a long time, and Max is running while you're going. Obviously, you don't want to compromise what Max is doing processing-wise. But you can have a lot of fun with this. So you can write a Max patch entirely in Max. You can save the Max patch that you wrote entirely from Max. You can load that patcher that you just wrote or any other patcher entirely from Max. So Max can sort of do all these things itself. That's the magic of scripting. In this lesson, I'm going to reinforce some of the ideas of the previous lesson about using Max to make abstractions that you then use in the rest of your program as if they were built-in objects by showing you one of the most sophisticated Max patches that I have been involved with in my life and one I'm still currently actively developing. That's part of a project that I'm really excited about called Ensemble Feedback Instruments. So this is a bit of research that I and several of my students presented at the New Interfaces for Musical Expression Conference in 2015 in Baton Rouge, Louisiana. And I've got the PDF file paper here. It's called Ensemble Feedback Instruments. So this is an 8-person group. These 8 authors were all members of a musical group that I founded called the Create Ensemble back when I worked at UC Santa Barbara. And the basic idea is that we have a bunch of instruments that we connect to each other in different ways. So I'll let you read this paper if you like. It's easy to find online. But I'll just give you a quick demo of what the idea is about. So basic idea is that we're all sitting here with all of our various instruments, and each of our instruments has an audio input as well as an audio output that are all connected through quite an impressive tangle of wires into a central computer that has one input and one output for each performer. So each of these instruments can take an audio input that it somehow incorporates into its audio output. For example, a commercial analog synthesizer, a super collider patch controlled over open sound control from an iPad that's running TouchOSC, a Raspberry Pi that's running a PD program that's being controlled by some potentiometers that are connected to an Arduino, a very, very cheap, very small, this is about a 3-inch wide analog synth from Korg called the Monotron, comes in a couple different versions, my own Max patch called Whistlespace. So the idea basically is that we can connect our instruments to each other in different ways. So for example, the output of my instrument could become the input to Hafiz's instrument, and then his output could be connected to the input to Tim's instrument, and so on. And we can go around, and you can probably guess from the fact that these are arranged in a circle that the fun really starts when Carl's output connects back into Matt's. So now we've made a feedback loop. And we could connect each person in 2 directions to the person on either side of them in the ring, or we could do the reverse ring, or we could have 2 rings of 4, or 3 rings, or some kind of arbitrary crazy topology, or I could sort of be at the center of everything. We call this the star topology, or we could be fully connected. And what that means is that these arrows are showing that the output of one person's instrument becomes the input to another person's instrument. So there's a Max patch that makes all these connections happen, and that's the patch that I'm about to show you. So one of the things that the Max patch does is it visualizes what's happening. So it can make a very dense sound, and the audience might be wondering who's making what sound. And so that's what this patch does. This visualization part, this is just a static screenshot of it. It's showing you the spectrogram, this is a spectroscope for each person. It's showing you the level with a meter of how much signal is going into each person's instrument, which we call the here, and how much signal is coming out of each person's instrument, which we call the say. So you can see in this static moment here that Hafiz's instrument was outputting more than it was hearing. And so these are some number boxes that are making an estimate of the gain difference between hear and say. So you see Hafiz has a positive gain because he's outputting louder than he's hearing, whereas Hannah has a negative gain because she's saying less than she's hearing. And it also is showing the topology of the ring, and it's showing what's connected to what. This is an object built into Max called matrix control that is good for turning on and off connections in a matrix. So here's a video of just a little example that we made, where we excite, we get into a ring topology, we add a sound into it, and then we let it go around the ring and eventually decay. Here's another example where we put a sound in and it's growing, and then somebody kills the sound, and so on. So there's a bunch of examples of things we can do. I'm not going to give you the full story about all this because I want to get into looking at the Max patch itself. So this code is all open source. You can find it on GitHub. There is a GitHub group called Create Ensemble, and there's a project called Feedback. So I'm going to go to that now. I'm going to go to my web browser, which conveniently is already on that URL. And GitHub is good for downloading source code. So I'm going to download a zip file that contains all these programs, and then I'm going to try to get Max open. So here's my downloads folder. So there's Feedback Master. I'm going to put that on my desktop and open it up. And inside it, there's a Max MSP subpatch that has all of the programs that we made. So since I moved from UCSB to Stanford, I have been co-directing the Stanford Laptop Orchestra, or SLORC. And SLORC just actually recently did a couple of performances using the same idea. So the most recent version of the patch is this one. So I'm going to open this version, SLORC ensemble feedback.4.maxpat. And here's the front page of it. So this front page is showing me all 12 of the players that are connected, and we can set whether each of these positions in the matrix is an I/O instrument, meaning that there's one output of the digital to analog converter that is making an analog output from a multi-channel interface that is feeding in analog into that instrument, and then that instrument's output is also going in analog back into the same numbered input of that interface and getting back into Max. But one of the things we learned is that sometimes people can't come to rehearsal, or sometimes people can't make the gig, and you've got all your topologies that are set up for, let's say, a 6-person group, but for this afternoon there's only 5 of us, and what we learned is that we need to be able to bypass. So maybe person number 4 isn't here right now, so we have a feature to be able to bypass them and replace them with a delay line of a given duration. There's this display patch that is actually more pixels than the size of my screen here that shows you all the stuff I just showed. This is a slightly updated version with a new font and a new color scheme. And then there's this matrix patch here that matrix control that sets all the connections that exist from one to another. So I'm not going to show you in depth every single feature of this patch, but I just want to show a couple of abstractions that are key to making this work. So one of them is this thing called display plus gain test. So you notice that this patch opens in presentation mode. That's important because we're going to later use it inside a bpatcher. So I'm going to go out of presentation mode and take a look at it. So what's happening in this patch? This is demonstrating a lot of the things I just showed you. So there's an argument. First of all, here's a comment that tells you how you're supposed to use it, and it says it's designed to be used inside a bpatcher whose argument is the instrument number, an integer. So here's a load mass that's got that, and we have a receive object, two receive objects, two receive tilde objects that are receiving the here signal for this particular one and the say signal for this particular one. And you can't actually put the number 1 on the inside of a symbol here. It has to be at the beginning, which is why I overwrite the receive name with this sprintf. So when we load, let's say this is number 7. So 7 comes out of this load mass, it goes through this sprintf, the message say 7 comes out, and then this receive is now listening to say 7. So this initial argument is just a sort of dummy, so you can see what's supposed to happen. So here's the here signal for this person, here's the say signal for this person. You can see that these meters are just visualizing the raw gain of the here and say signal, and that the spectroscope is visualizing the spectrum of this say object. We also are somewhere else in the patch, we're going to send that 7-name is somebody's actual name. I'll show you where that happens. That's over here in config instruments. So here's a bunch of configuration that happens, but one of the things that it does is it can set the name. So here are the 12 students who performed this piece in SLORC recently. So if we click on this, remember the semicolon is short for send. So semicolon 1 name Trajit is saying that send to the 1-name destination, the symbol Trajit, and then semicolon 2 name Jack, and so on. So this is what's sending these 12 names. So you can see here I receive the 12 names on the front page, and we see the names over each instrument, and also inside the display you can see those 12 names in the correct place as well. Let me show you some more of display plus gain test. So one of the things that it's doing is it is taking this meter, which is not only visually depicting how loud the signal is, but the meter object will actually output a number that's saying what it came up to. So for example, if you've got a sound file you're playing, it's not only demonstrating graphically what basically how loud the signal is, it's actually a peak level indicator. So within the interval of some number of milliseconds, it's finding the maximum absolute value of any audio sample. That's what makes it a peak level indicator, because it's looking for the maximum. So within each of these 50 milliseconds, there's some number that's the maximum sample value, and that's actually coming out as a max event. And so this object is using that. So there's some peak value that comes out, and we're converting to decibels. And first thing we're doing is we are sending the message, first thing we're doing is we're subtracting those two from each other. So that's what we call the instantaneous gain estimate. So remember when we were looking over here, when you're looking over here at the visualization, you can see that there are these numbers that are telling us that, in this case, Hannah is really decreasing the gain. She's outputting less than she's receiving, whereas Hafiz is increasing the gain. He's outputting more than he's receiving. So this is the part that actually does that. And it's kind of a clever thing that actually Carl Yerkes came up with, of just taking the output of this meter, converting it to decibels, and just subtracting the two. Just literally saying, in this moment, your say is 14 decibels greater than your here. So what do we do with that? We put it through an object called mean that is finding the average value over X amount of time, and every 500 milliseconds we clear it. And then we take every 4 of those values that come out of there. So this is happening every 50 milliseconds or so. And then every 4 of them is every 200 milliseconds, so that's a slower mean. And every 4 of those is every 800 milliseconds, that's an even slower mean, and so on. So these are more averaged, smoother, more long-term estimate. And in the end, we use the fastest one and the third fastest one. I'm looking at this very faint pink outline that's showing me which of these are in the presentation. So that's what these two numbers are. So this number is changing more rapidly than that one. So this object, display plus gain test, it defaults to presentation mode. It puts all its stuff up here in the top of the window, and it's meant to be used multiply. So let me show you the next one, which is 12 display plus gain test. So I have Max running, and so there's a stereo mic on this laptop that I'm using, so you can see it's showing the spectrogram and the meter of my voice as I talk. And let me show you how this works. So this is, if I open this, let me make the window a little bit shorter so that we can get to the bottom of it. So if I go out